Okay, ladies and gentlemen, so in this segment we're going to be looking at how we can take vectors that are at an angle and use the algebraic or mathematical method to determine the resultant displacement. So in order to do that, what we're going to have to do is we're going to take our individual displacements and we're going to have to find the x and y components. So I'm going to find the y components for each. And you can see here I've labeled them appropriately. So the first displacement, the y component is d1y. For displacement 2, d2y, etc. We're also going to find the x component as well. And once we find these different pieces, we're going to take all the x's and y's and find the vector sum. So we're going to add up all the y components, all the x components to get an overall. So my overall y, we'll just call it dy here, is equal to the sum of d1y, d2y, and d3y. So from here to here. So we have this component here. And for the x, we're going to label the overall x dx, and it's going to consist of d1x plus d2x and d3x. So we're going to end up with an overall y and an overall x. And what we can do with these is to draw a sketch, making a little right-angled triangle. And then we can figure out the resultant displacement using the Pythagorean theorem. So it's equal to the square root of dx squared plus dy squared. And I can also find the angle of the vector. Remember, it's measured from the beginning. So the angle of the displacement is determined using trig. This is going to be my opposite over the adjacent, dx over dy. And we get our final answer. So what we're now going to do is to look at a specific example. So in this situation, I'm going to have an airplane flying 75 kilometers south 30 west and 55 kilometers north 60 to the west. So I'm going to draw a little sketch of each of these vectors. So the first vector is going southwest, and then the second vector is going northwest. And I'm going to try to figure out the resultant using the mathematical approach. So as I said earlier, the first thing we have to do is figure out the x and the y components. So we're going to look at each vector individually. The first vector to get the y and x, and the second vector to get the y and x. Now notice it gets kind of confusing having all of these overlapping vectors. So what we tend to do is we tend to draw these vectors separately. So in other words, they're going to look like this. It makes life a little bit easier. So vector 1, remember, is going 75 kilometers and is being measured from the south 30 degrees to the west. Vector 2 was 55 kilometers. It was measured from the north 60 degrees towards the west. And what we're going to do is to determine the different components. So for example, for vector 1, to get the d1x, d1x is opposite to the angle. I know my hypotenuse, so I can take sine 30 times 75 kilometers to get my x component. And I end up with 37.5. So I figured out how far west we've gone here, so the west component. Similarly, for the y component, it's the adjacent side. We know the hypotenuse, so I can take cos. So use cos 30 times 75, giving me 65 kilometers south. So I figured out that this vector is going 65 kilometers towards the south. So remember to always put the direction in square brackets for these when you're doing the components. And double check that the x is going to be east-west and the y's are going to be north and south. I do the same thing with the second vector. So here the adjacent side is d2y, so you can use cos. And the opposite side is d2x. I'm going to be using sine. So we've got these different components. Now that I have those components, we're going to find the sum of them. So I'm going to find the sum of the first and second component in x. And we have one overall x that we get. So we're going to end up with 85.1 kilometers to the west. Both d1x and d2x went to the west. So overall, we have a large west component. Now in the y, one of the vectors went south, so d1y went south, but then the second vector went north. So when we add these two together, we end up with an overall south vector of 37.5 kilometers. So now I know the overall x and the overall y. Next thing we can do, we can draw a little diagram. So I'm going to draw a diagram, make a little right angle triangle to figure out my dr. So in this case, I drew west, and then I drew the south. I could have also done the opposite, where I drew the south first and the west. It makes no difference. You can see on the workbook page, we do it both ways. If I was to do it this way, so I drew my sketch, my two overall vectors, I'm going to figure out my resultant. And the way I do that is to use the Pythagorean theorem. So to get the size of the dr, it's 85.1 squared and 37.5 squared. And you end up with 93. Now, to get the angle, I'm going to be measuring the angle from the beginning and be using the opposite side and the adjacent side. So in this case, it's going to be 37.5 opposite over adjacent 85.1. And when you do the tan inverse, you get 23.8 degrees. So the overall dr is 93 kilometers west, because we're measuring from the west, 24 degrees towards the south. And we've got two significant digits because that's what we're limited to in this particular problem. So you'll find a similar problem in the workbook. And again, I show you both possible answers. There's two possible answers. The other one, it would be 93 kilometers south, 66 degrees to the west. Exactly the same, just a different approach. Okay, so that's it. What I'm going to do in the next segment is to actually show you a specific example.